At the beginning of the last class, I think we discussed about the uh, random processes and specifically about the multiple random processes, where there are basically two signals or two different random processes that we are considering. And we use the joint behavior of such random processes. And in order for us to analyze the behavior, we have to use the cross correlation, cross covariance, and similar statistics to study the statistics or the behavior of the random processes and see the joint behavior of those random processes. So we discussed about how the cross correlation can be defined mathematically, and the cross correlation can be defined as the expectation of the product between the two different signals X and Y. And we discussed about how by looking at the cross correlation, how we can define the orthogonality between two random processes. So if the product between the autocorrelation is zero, or I mean the product between the two processes and its expectation is zero, we can say that the random processes are orthogonal. So by using this condition, we can check whether the random processes are orthogonal. If the autocorrelation in here actually it is cross correlation, the cross correlation value equals to zero, we can say that the random processes are orthogonal. So if the random processes are orthogonal, that means that even like if when you're having two random signals, there's no point where both the signals are uh, uh, working uh, working together, whereas they function and um, they work, or the signals can propagate on their own. So even if there's a product between them at some point, or if there's some overlapping between those two signals, those two different signals, the effect, uh, the outcome of that product will be zero. So that is what is mathematically defined in here. And this orthogonality behavior or the orthogonality quality is used for applications such as transmission of signals in the telecommunications using the OFDMA multiple access scheme. So there we are combining multiple random or multiple data signals, which can be random, together, and then we are transmitting them over the uh, over some over a certain time and or maybe different frequencies. So when we are combining signals with different frequencies, there could be some interference from one signal to another signal. And in order for us to avoid such kind of interferences and reduce the interference, we consider this orthogonality behavior of random signals. So uh, we try to use signals which are orthogonal to each other when we are trying to combine different signals. Those different signals are orthogonal to each other, then the effect from one signal to the other signal can be minimized. Anyway, like orthogonal processes show this property of their cross correlation value being equal to zero. Apart from that, we described about uh, how these processes right we described about the case where these two random processes can be independent as well. So independent random processes and their conditions we discussed, and how they can be mathematically defined. Just like the case where we discussed about the independent random variables, uncorrelated random variables, and orthogonal random variables, we can we can give a similar definition to the independent and uncorrelated random processes. Just like random variables, these random processes also can either be independent or uncorrelated, then orthogonal likewise. So how we can find them is by using the mathematical definitions that define the independence uh, or like uncorrelatedness between random processes. If we can show that they satisfy that certain criteria, then we can show or we can prove that those random processes follow a certain behavior. So we learned about the independent random processes, uncorrelated random processes, and then we discussed about um, how we can define the autocorrelation function uh, for a random process, and how we can define that autocorrelation function for random process using mathematical definitions. The autocorrelation function can be uh, defined as the expectation of the product between random process xt1 and random process xt2. So if there's some time difference between the time instances that we are comparing, or we are considering when we are calculating the autocorrelation function here, uh, and so I mean, depending in here, of course, like what I'm showing is basically the autocorrelation function definition for a IID process. So in that case, since the random processes are independent, you can use the theory that the autocorrelation function can be found by taking the multiplication of the two uh, of the expectations of the two random processes. So what if the time instance is same? So that question I think one of the students have raised. So I would like to discuss about that, since there's a question there. So if the time instance is same, you can actually find uh, find this output using the definition that we use to take the autocorrelation value. So the autocorrelation value can be taken by taking the product between the one process and the other process, and uh, by simplifying the expression. So in here, if the time is same, we can when we are taking the autocorrelation value for a IID process, the when you take the autocorrelation value, I think that get the you get the value. You just get this singular value. I think this should be only ext1 squared. So I don't know whether I can edit this now. Um, so Okay, I think I will look into it. I need to verify using the math, some, um, I need to verify that using some equations. So, anyway, like if a certain random process is independent, the the definition is that the autocorrelation function that uh, that we can define as the expectation of the xt1 and xt2 will be the product between the two random processes. So if they are independent, that means they are uncorrelated as well. And for uncorrelated processes also, this is the same. So for independent and identically distributed, uh, the uh, the PDF function at each time variable is same. So the expectation of xt1 and expectation of xt2 are same. On top of that, since they are independent, the expectation of the product of the two random variables t1 and t2 uh, is equal to the independent product between those two variables. So when we take the um, autocorrelation value of the two signals, I mean, so when we take the autocorrelation value of the two random variables, T1 and T2, we can say by definition that if the time value is same, time value is say, let's say if it is different, then the product should be taken as the output, right? So that this should come here. So it is, I think, same as what we discussed. So if the time value is same, is what we want to try to find out. So if the time value is same, that means that the same uh, function is actually getting multiplied here. So it should be xt1 squared actually. So if the time value is same, the autocorrelation value should be ex squared t1. So I think uh, the sigma part is it should not come. So this autocorrelation value equals to basically only this term. So so I think you can consider this as the uh, this as the autocorrelation value, and like there's no sigma term that is getting added to this one. So I think that would be the basic difference I think that I want to make. So I think the sigma part should be uh, neglected, and only this term should come as the autocorrelation value when you take the same time instance into consideration. Then this, of course, is the same as before. So I will just write it. So the autocorrelation value, when you consider two different time instances of the random process, will be equal to the expectation value of the two random processes, and taking the product independently. So autocorrelation value can be taken like this uh, for different cases like this, if the random process is independently and identically distributed. Uh, so we can do the same thing for the covariance also. In the last class, I think we discussed about the covariance. So for the covariance also, we can define the mathematical definition. So if you consider the covariance value of two random variables, uh, which are um, which are uncorrelated, then we can define similar, definitions for the uncorrelated case also. I think we discussed that. So we discussed the cases under time being equal and time being different. If the time is equal, the value of the covariance between the two random variables t1 and t2 equals sigma squared x t1. So if we are considering one time instance, it can be either T1 or T2 here. So the variance of the signal will be the value of the covariance at that time. So uh, yeah, so the covariance will give the variance between two time instances. If the time instance is same, then the variance at that specific time instance will be considered as the covariance value. Then, if the time instances are different, then the covariance value is going to be uh, 0 if the process is uncorrelated and independent. So, uh, so that is how it is defined uh, for a uncorrelated and independent process. So the covariance function is defined mathematically using this expression also, where uh, where you can define it as the uh, 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 product as the expectation value of the two random processes xt1 and xt2 minus the uh, singular product between these two processes. When we take this expression into account, we can see that if the process is independent, then this expression will be same as this one, right? So because they are same, the output of the covariance function, or the value of the covariance function, will equal to 0. And that is the reason that we obtain a 0 in here when we have time instances different. So the covariance value can be defined like this. and the autocorrelation value can be defined like this. So the sigma term does not get added up in here. So there was a mistake in the last class when I defined the autocorrelation function of a random process which is uncorrelated. So if they are uncorrelated, then the output will be like this when you consider the same time instance, and the autocorrelation value at the same time instance will be equal to this expression E x squared t. So it won't have any sigma term added. So please note that. So covariance value will be as given in this in this definition. So I think that's all regarding the concerns I think we had regarding the last classes content. So I hope other things are clear and they are not having you are not having any concerns regarding the other sections. If you have any questions regarding these sections, you can let me know. So you have this note with you. You can refer that. So so in the last class, after talking about the different types of random processors, uh, we then came into a point where we discussed about uh, the stationary random processors, right? So we have already discussed about the independent identically distributed random variables, uncorrelated random variables, orthogonal random variables. Now we have discussed about the stationary random processes. The stationary random processes are processes that have that show statistics, or that show behavior which uh, 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 in a way that the statistics of that random process is constant over the time, right? So the statistics of the random process uh, remain constant over the time, right? So I think I will try to obtain, I try to again see whether we can have a random process. Yeah. So in here we have the random process defined using a figure. So in this process, if the statistics of the random variables that we define at time instance, uh, let's say T1, uh, is equal to the random variables at T2, T3, likewise, if the statistics of other time variables will be equal, or if the statistics of the random process stays constant over each time variable, we can consider that process as a stationary process, right? So generally that is the case, but there are different types of stationary processes. So we discussed about two main stationary processes, basically about the strict sense stationary process, or we call as SSS. Then we discussed about the wide sense stationary process, so WSS. In the strict sense stationary process, the statistics of the random process, right? So what I mean by statistics is basically the mean value of the time variable, right? So if we take a random process, right? If we take a random process, we can get different outcomes uh, of the random experiment, right? So if we consider a scenario where we are receiving a call uh, and we are receiving multiple calls, we can consider one of the calls as one realization, and that uh, and likewise we can have different calls. For those different calls, we can plot the variation of the signal power against the time. So if we do that for all the calls that we have received, we can create a set of outcomes, right? Or set of outcomes, or set of realizations. And the set of realizations we call as the ensemble of the random process. and that all these realizations, uh, uh, the set of all these realizations we call as a random process, right? And if we want to study the random process at some point in time, we we try to get the probability density function at that certain time value, and that probability density function can be any specific distribution function. So if we consider receiving phone calls, the signal strength of the uh, phone calls at a certain time instance are said to follow a Rayleigh distribution. So using this Rayleigh distribution, we are able to find the statistics of the random variable that is defined as at this time equals 1 second. So the statistics are basically the mean value of this mean value of all the values that we can observe at this time equals 1 second, uh, and variance values, and then autocorrelation, autocovariance. Those things are the ones that we can actually try to find regarding this random process. So when we take one time instance, we can find the mean value of all the amplitudes that we have observed under that time instance. Let's say it's 1 second. So the amplitudes of all the different realizations we can consider, and we can find the mean value of all the amplitudes, right? And so that can be done easily using the probability density function also. So if we have the probability density function, we can use the probability density function to find the mean value of the amplitudes, right, at the certain time instance. So this the statistics that we can find regarding a certain time instance is known as the statistics of the ensemble, right? So ensemble average means the average value of, I mean, let's say in here amplitudes, average value of amplitudes that we can observe at a certain one specific time instance. So we can do ensemble. We can also find, similar to the mean value, we can also find the variance, which across the same time instance, right? And then we can define it, and then we define it as the ensemble variance, right? Apart from that, we can compare two time instances. And for comparing two time instances, we use statistics such as the autocorrelation and autocovariance. The meaning of using autocorrelation is to compare 2 points in the random process, and then we can compare 2 points in time across the random process. So we can consider all the values that we can obtain for one time instance, then compare that with all the values that we can obtain under another time instance. So autocorrelation values give us a uh, idea about the values that idea about the two different points in a random process. So the stationary random processes are defining uh, a certain set of random processes that has same statistics over all the time variables or all the time instances, right? So the statistics that we obtain here at t equals 1 second is if it is equal to t equals 7 seconds, and if it is equal to all the rest of the time instances, we call that kind of a random process as a stationary random process, right? So if the PDF of the random variable is not changing over the time instances across the time domain, we can call such kind of a random process that has such kind of properties as a stationary random process. So a stationary random process has statistics that are not affected by the shifts in the time. Apart from that, there's this simpler version of the wide sense stationary process, which is a simpler version of the strict sense stationary process is known as the wide sense stationary process. So, wide sense stationary process is a simpler version of the strict sense stationary one. So the reason is that the strict sense stationary process is defined for statistics up to the nth order. And strict sense stationary processes are not realistic in the nature. Most of the random processes that we have in the real world, they they are very random, that the statistics do not remain constant over all the time instances and up to the nth order. So in cases where we want to consider more realistic uh, random processes, we will consider this wide sense stationary definition and use that theory to study the properties of the certain random process. So for wide sense stationary random process, we have statistical properties constant up to the second order, right? So the statistical properties such as mean value, variance value, they remain constant over the time values in the wide sense stationary processes. So up to that point, we discussed in the last class. So the statistics up to second point are considered constant under the wide sense stationary process. So in today's class, we will have to go ahead with that point, and we will discuss about the next random processes that are important under this stationary random process topic. So if you have any questions up to this point, you can raise them. I will start the next section. So do you have any questions? So I think I will discuss with you about the ergodic random processes next. Ergodic random processes. In the last classes, I think I discussed a little bit, or I just mentioned about this word ergodic. So ergodic random processes are random processes that that have special properties. So the special property in here is that the ensemble average of this process is equal to the time average of any single realization of the process. So I will explain that using a certain example. So if we consider an example where we obtain a call number one, let's say a call number one is obtained, and we see the signal power varying randomly across the just like this, and then across the time domain, let's say the amplitude is varying. So if we so this is the amplitude of the signal. If we consider another call, call number two, then we can also for that also we can obtain some kind of amplitude variations of the signal, right? Once we measure the signal power at the receiver end. So these two signals are not similar, right? They are random signals, and call one is a random signal, call two is another random signal which we obtain. So uh, the however uh, both these calls are received from the same random experiment. The call one will be one realization of the experiment, and call two will be another realization of the experiment. So we are considering two realizations of the same random experiment. Uh, the ergodic random processes. In order to explain that, I will first need to explain about the ensemble average. So ensemble average is defined for a certain time instance. Let's say it is 1 second, right? And then we take the average of all the amplitudes that we observe at this 1 second, and we obtain the probability density function that can be observed in that time instance. So the probability density function that we can obtain is basically the Rayleigh distribution, since we are considering the phone calls. So for wireless communication signals that we receive over a certain wireless channel that faces interference or non-line of sight conditions, the signal strength will follow a Rayleigh distribution. So this is something that is theoretically accepted regarding the signal power. So the signal strength at T1 time instance can be uh, denoted as one random variable. That random variable we denote as xt1, and its PDF function we can denote using uh, the its PDF or its probability values. We can define the probability density function, and then we can do that for all the other time instances as well. And if we find this Rayleigh distribution probability density function is seen at each time instance, then we can say that the process is a stationary process. So if these two probability density functions that we observe, right? Not only these two probability density functions, but also we can consider each of the time instances uh, that we have in this sequence, and we can consider all the probability density functions that we can observe at each time instance. So we can consider time instance 10 second, right? So time instance 100 second, or the time that this signal stops. I mean, the signal stops. Up to that point, we can find the values of the uh, probability density function for each time instance. For, so in here for time seconds, time equals 5 seconds, we can find the probability density function, right? We can find the probability density function for t equals 5 seconds, then for t equals 1 second. Likewise, we can find. If we observe that these probability density functions are equal or same, then we say that such kind of process is a stationary process, right? Such kind of process is a stationary process. And further, if we find that the time realizations or the specific realization that we obtain in here, this sorry. So if we can find uh, the the distribution of the amplitudes and their probability for this specific realization, and we can draw that right. If we can draw the amplitude values, uh, and we can find the probability of a certain for a certain amplitude to occur, right, over all the time. So this is uh, the amplitudes that you can observe over all the time instances time the t, and this x is related to this sig call 1. So amplitude that we measure here is related to the call number 1. So I put x1 here, and then we can find the probability of uh, probability function for that amplitude. So we can plot the probability for this certain x1 amplitude to occur. If we can observe that that probability density function is following a certain density function, then we can draw that. So we can obtain the probability density function for the amplitude that we can observe for all the time instances, and then we can draw the probability of it occurring. So for each single realization, time realization, we can find the distribution of the amplitudes, and we can draw the certain specific random uh, uh, specific distribution function, right? So if so we can, right? So what I did here is that, like so for in time domain I find the PDF value, right? Over the time domain I find the PDF value, and I try to find that for each realization. So this is for the first realization. So this second plot is for the second realization. And if I observe that these two realizations are same, and therefore, like, I can say, okay, the PDF is same for both these two realizations. And like, if I see that it is the true situation for all the possible realizations of the random process, I can say that the time averages are constant over all the realizations. So if I do the time, if I try to find the time average for all the realizations, and if I find that the time average is same, time average value, time time average is same for each single realizations, for the time, uh, right, the PDF of each of the single realization of each single realization is the PDF of each single realization is same. Then we can say that uh, the uh, they all these different realizations have the same PDF. So if by any chance this PDF of single realization is also same as the ensemble average, that means that this PDF value that we get for the time domain, if it is equal to the one that we get uh, over the one ensemble, then we call such processes as ergodic processes. So ergodic processes means that basically if we obtain a realization average or a realization PDF function that is equal to the realization ensemble average or ensemble PDF. So if that is the case, that means that whatever the PDF values you get over the time is equal to the whatever the PDF values you get over the ensemble. So in that case, that ergodic random processes will be defined as a process that that has ensemble average equal to time average. Right? It's ensemble average equal to the time average. So the ensemble average we can denote using this EXT, and then we can denote the time average using an integration over the time domain. So when we take the integration over the time domain, if the signal that we consider is a very random process, then its average cannot be found without considering the non-periodic manner. So we normally try to find the average of a periodic signal using this integration, where the limits go from minus t over 2 to plus t over 2. Uh, and where the amplitude of the signal is xt, and we integrate it over dt. So the time value should go to infinity in order to show that the period of that signal is actually infinite. So anyway, from this expression we can find the time average of a single realization and of a specific realization. We can find the time average of a specific realization using this integration, and this will be equal to the ensemble average. So if we have this condition satisfied, we can call that that process is a ensemble. That process is a ergodic process. So if that process is a ergodic process, then we can have the advantage of finding the statistics of only one realization and using that to determine the properties of the entire random process. So this is a ergodic random process. Ergodic random process is useful because we can observe only one realization, right? Statistics of a single realization uh, is sufficient for us to obtain the statistics of the entire ensemble, right? So we can study the entire ensemble using one realization. But that is basically regarding the ergodicity or ergodic processes. So do you have any questions? With regard to the other properties of a ergodic random process, the ergodic random processes, we can study the uh, autocorrelation of a ergodic random process. So ergodic random process, we can study the autocorrelation of a ergodic random process. So I will write it in here, autocorrelation of a ergodic random process. So autocorrelation function we can define using this time instances that we consider, and then if it is a ergodic random process, basically ergodic random processes are actually like processes that have same statistics over the time instances, right? So in that case, like since this ergodic random processes are part of the uh, right, so it is following the same uh, behavior as a wide sense stationary process as well. So I will try to explain that in here using a diagram. So if we have different random processes, right? So this is a if this is a random process, uh, so a subset of a random process will be the strict sense stationary processes. So inside these random processes, all the random processes, we can have a subset of uh, strict sense stationary processes. Inside the strict sense stationary processes, we can have a subset of wide sense stationary processes. Sorry, inside the wide sense stationary process, which is a more relaxed version, we will have a set of like strict versions of random processes, which are strict sense stationary random processes. And inside these strict sensation random processes only, we have these ergodic random processes. So if you can understand, it would be like it's very hard to find the ergodic random processes because like the ergodic random processes will be subset of the all the other random processes that we discuss, which are wide sense stationary process and strict sense stationary process. So we have to have a situation where all these WSS and SSS properties are met in order for us to find a ergodic random process. However, ergodic random process is therefore anyway a process that follow the condition that the statistics will be constant over time, which means that the autocorrelation function of a ergodic random process will only depend on the time difference between the time variables. So if we consider the autocorrelation function's value will depend on the time difference between T2 and T1. In here, the time tau is defined as T2 minus T1. So anyway, the autocorrelation function can be defined by the difference between the time differences T2 and T1. And then in that case, um, the uh, so this RXX tau value we can define as the ensemble autocorrelation value. We can so we in order to take into account the ergodic random processes consider ensemble average equal to the time average. So if we take the autocorrelation value between two time values or two instances in the time domain, let's say T1 and T2, the definition will be uh, as given as a the definition can be given as a integration between 2 points in the time domain. We can further write this as t goes to infinity. So what we are trying to find is the we are trying to find the time average of the signals, right? So let's say this is the time average of 2 points in the ergodic random process. So the time average we can uh, find using this integration, where the integration will happen between 2 points, T1 and T2. So let's say T2 occurs in this point where T1 minus tau gives you the T2. So by taking this integration, uh, we can find the uh, I mean, this integration will give you some output. And in order to find the time average, we need to take the integration where we set the limit of time reaching to infinity, and then we divide by 1 over t, and then take the product with xt1 and xt minus tau. So this whatever the duration of the time instances you take as the limits of this integration. So this expression will give the time average over the time domain. So it is seen that these two expressions are equal, which means that the autocorrelation function values at T1, T2 is equal to the time average uh, or the average value that you can get over the time domain as well. So I think I will try to uh, explain that using mathematical expressions. So in here, you can find the average value. So over the time domain. So this one we have taken over the ensemble. So the autocorrelation value taken over the ensemble is equal to the autocorrelation value taken over the time domain. So that is basically regarding the ergodic functions, ergodic processes. So then we have to consider, yeah. So I think uh, we will uh, we will see that uh, by that point we will be able to conclude the ergodic processes theory. Before concluding, I will say that uh, if a certain process is ergodic, it is easy to find the properties of the random process. Uh, Studying the PDF of the random process is easy, which means that in ergodic random processes, the once you know the PDF function of a single realization, you can use that to find or predict the realizations. I mean, once you know the PDF of the time realization, you can use this to uh, obtain the ensemble PDF as well, because ensemble PDF and time domain PDF are equal in ergodic. So if you know the PDF of a single realization, that is sufficient for us to predict the ensemble PDF. So if a random process is not ergodic, if a process is not ergodic, then it's difficult to find the PDF of the random process easily. Not easy. Not easy to find the PDF of the random process easily, because we need to consider the ensemble, and we need to find the ensemble average. Finding the ensemble average is difficult actually in real world, because mainly we have a random process that has like a large amount of realizations. In that case, finding the average of all those large amounts of realizations is difficult in practice. I hope it is clear to you, right? So, up to this point, do you have any questions? So, I believe I will explain this again. So, if we have a process which is not a ergodic process, then in that case, that when we try to find the PDF of that random process, it is not easy to find the ensemble average, right? There could be large amount of realizations possible from the random experiment, right? So if we take the figure that we drew here, the, I think if we go here, if we can consider random process, which is not ergodic, then there could be multiple random realizations that are obtained. Like if we consider this scenario with multiple calls, we are receiving calls, call 1 up to call 10, up to call 100, call 1000. We have 1000 calls, for example. We need to measure the amplitude at each time instance 1 second of all the realizations to find the probability density function of that certain time. So if we have 1000 realizations, we have to do this for 1000 times. We have to measure the amplitudes. And then afterwards, we have to calculate the PDF. So in order to calculate the PDF, you need the values of all these amplitudes at a certain time instance. So it could be 1 second, it could be 2 seconds, 3 seconds, likewise. So you need to do the experimentation for a large number of times, and you need to perform repetition in number of repetitions to obtain value at a certain obtain the PDF value at a certain time instance. However, if you have a ergodic random process, and if you can ensure that it is a ergodic random process, then it shows that it says that you only need to consider one time realization, that means one realization. Then you can study the statistics of that one single realization, and using that statistics you can define the ensemble statistics, right? So basically, uh, so basically in here, when I tried to find the autocorrelation of the random process, what I tried to do was that I tried to find the autocorrelation of one single realization and then equate that to the ensemble's entire autocorrelation value. So without going through all the ensembles separately, I can find the autocorrelation between 2 points in the single realization in the time domain, and then use that to find the autocorrelation between all the different realizations in the random process. So if I may to draw that diagram again, I will show you using a small diagram. So if there are maybe several realizations of a random process, the random signals could be of certain random form. And then if we try to find the autocorrelation value, uh, autocorrelation value can be found between 2 points in the random process. So let's say that up to this random process has up to 10,000 realizations. There are 10,000 realizations for this random process. If we are trying to find the autocorrelation value, then we need to find the amplitudes that we obtain for each for two different time instances that we consider. So if we consider T1 and T2 time instances, we need to consider the amplitudes that we obtain for all the realizations under that T1 time instance. And then we need to compare that those amplitudes with the T2 time instance and its amplitudes. So for T2 also you have to consider the amplitudes that you can obtain. For T1 also you can find the amplitudes that you can obtain. And then for all the realizations we can obtain amplitudes like that. And then once you try to find the autocorrelation value, you need to take um, uh, the a- the average values of these amplitudes at a certain time instance, and then consider the average value at another time instance, and they take the product, so on. So this that process is requiring you to find the amplitudes of all the realizations in the random process. So there could be some random experiments that about which we don't have full information about, which means that there could be like 1,000 times or 100,000 times of realizations, and we might not be able to observe such kind of realizations. However, in a case like that, if we can prove that the random process is an ergodic random process, then we can actually use this only one single realization, and then we can find the statistics of this one realization. So the statistics of autocorrelation was the one we were discussing earlier, and that we were trying to find the autocorrelation value in here. So autocorrelation value of a single uh, autocorrelation value of a single realization is found, and it is made equal to the ensemble autocorrelation. Right, so autocorrelation that you can observe by considering all the ensemble values is equal to the autocorrelation value that you find by taking the autocorrelation value uh, along the time domain axis. So I hope it is clear. So you only need to consider one time realization and its statistics to determine the statistics of the entire random process if you have the ergodic random process. Right. So in here, what I discussed was about the autocorrelation function, and the autocorrelation function of the entire ensemble can be found by taking the autocorrelation of only one single realization. Up to that point, I hope it is clear. So that is what I have discussed up to this point. So similarly, we can do the same thing for other parameters as well, such as mean value, variance value, and we can check whether those mean and variance values, are, uh, I mean, uh, if it is the ergodic random process, the mean value along the time domain axis or along this one single realization uh, will be equal to the mean value of the ensemble variable. So what happens is that if you have the mean value of a single realization, you can consider that the ensemble mean also is same to uh, the single time realization mean. That is basically regarding the ergodic random processors. So I think that is enough for the ergodic random processors. So uh, right. So before going further, I will discuss with you uh, one sum with you, and I will ask you to complete the rest of the sum in your own free time. So I in the last class, I think I told you that I will give you some kind of a assignment to do in the LMS, but I was not able to upload that one. I mean, I'm talking apart from the uh, MATLAB assignments that I have given. I want to give another assignment. That one I was not able to upload to the LMS last week, but I hope to upload it in this week, this upcoming week, and then you can do the assignment work. So now I want to discuss about one uh, sample question. So this is with regard to the wide sense stationary processors. So suppose that there's a discrete random process, right? There's a random process which is defined in the discrete time. So the discrete time random process is defined using a certain mathematical model. So it will be like this. So Gn equals A sine omega naught n plus B uh, cos omega naught n. So in here we have uh, the omega naught parameter and n parameter. So n is the discrete time variable, right? So this is the variable. N is the variable. W naught or omega naught is the fixed value. It's a fixed value that defines the frequency of the signal. So if we want to find, another data are given in here where A and B are independent, where A and B are independent uh, random variables. So A and B are independent random variables, and these random variables have zero mean. A and B random variables have zero mean, and they have variance of sigma squared, right? A and B random variables have a variance of each have a variance of sigma squared. Uh, the omega naught is a fixed value, fixed frequency value, and n is the time index. So n is the time index. It could be 1, 2, 3. Likewise, it could have some value. So what we want to determine here is that we want to check whether this process that we have defined in here, this random process, whether it's a wide sense stationary process or not, right? So first, there is one section about asking us to find the mean and the autocovariance of the function, right? So first we need to find the mean and the autocovariance of the random process, right? We have to find the mean and autocovariance of the random process. So first finding that is the problem. Afterwards, after you find these mean and autocovariance functions of the random process, then you need to determine whether this random process is a wide sense stationary process or not. So we have to determine whether this process is a wide sense stationary process or not. So those are the things that I want to discuss about this example. So first of all, we will discuss about how to solve this one. So if so you also can follow up. I think it will be good, but I think I will try to keep the question in here and then maybe try to solve that on the left side, right side of this board. So First, we will look at the first concern. So we have to first find the mean and the auto covariance of the random process, right? So in this function, we can see that there are multiple constant variables. The constant variables are basically omega naught. So mean of Gn. Okay, so can you try to find the mean of the random process Gn?
For the omega naught n, ma'am, is it multiplied by n or just omega naught n, like omega naught 1, omega naught 2, something like that?
It's multiplied by
Okay, thank you.
omega naught n. It's like a fixed value. Omega naught is a fixed value.
Thank you.
So you can just take it as a product, like omega naught n. It's just one value. It could be like omega naught could be some value like six, something like 6n, right? So this will be like 6n, 3n, like that. So Gn is a sine omega naught n plus b cos omega naught n. If we want to find the mean value of this Gn, we can find the expectation value on both sides. Expectation can be divided into the two terms. Since expectation operation is a linear operator, we can separately find the expectation of the two terms.
Question, ma'am. When you said zero mean, is it uh, A and B are zero mean random variables? Is it?
Yes, A and B are zero mean.
Okay, thank you. Then is the mean for Gn is zero?
Sorry,
Mean for Gn, is it zero? Is,
mean
no,
for Gn.
no, okay. Thank you.
You can try to find. I also will try to compute it. So when we are proceeding here, we can consider the assumptions that are given here in this question, that A and B are independent. If A and B are independent, then the A and independent and zero mean. So zero means EA value is going to be zero. EB value is going to be zero. So A and B are zero mean. So when we uh, try to see this expression, we can add the expectation operation into each of the variables separately. So if we uh, rewrite this as EA into the rest of the expectation, we can write as sine omega naught n plus EB and E cos omega naught n. Since we have this property that EA value equals zero, we can make this zero. Apart from that, when we take the expectation of this term, this sine value of this omega n, when we consider the values that the n can take, n is a index that can take discrete values. So it will be having some discrete values from, let's say, from 1 to some kind of a constant or some kind of a ending capital N value. So there will be some distinct value at which this n is ending. So the values of n are deterministic. We know the values of n to be some kind of discrete values. So this sign values of those discrete values will be some deterministic value. So because of that, this whatever this expression in here, sine omega n, will be a constant value. So you can take it out from this expectation operation. So this expression sine omega n, sine omega naught n, can be considered as a constant entire term, and then we can take it out from out as a constant. So we will consider it as a constant value because the omega naught value is a fixed value. N value is a value which is like 1, 2, 3 something deterministic, and its value also can be I mean the overall if we take sign values of omega naught n, once we know the values of n, we can substitute and we can find the values of sine. So that value that we get as the output of the sine function will be a deterministic value. So that deterministic value you can find based on the n value. So uh, so expectation of that constant value that you will get as out of the sine function, you can consider as a constant value. So that you can take it out from this expression. The cost value also will have a constant value, and we will be able to simplify this expression in a format like this. And therefore, these two terms will be deterministic values. Uh, so so sine value, cos omega naught n value, those will be deterministic values. They will be having some kind of a determined value. So the EB and EA are anyway zero. So because of that, we can consider that this entire product is zero, and that will result in zero as the output. So the mean value will be zero, and we can consider that in this random process Gn, the mean value is zero, and it does not depend on any specific time instance. Doesn't depend on specific time instance of n. So similarly, we can find the other factor, which is the autocorrelation value. So autocorrelation value we can find uh, by taking the expectation operation. Uh, However, like if we uh, if we are trying to use the effect of the uh, mean of the random variables. So in here we are trying to we are given the fact that A and B are random variables that have the zero mean. So in order to take that into advantage, in that into account, we can consider the statistic of autocorrelation, and then we can find the autocorrelation function. Sorry, autocovariance function. So we need to find the autocovariance function. So as anyway, it is given from the question as well. So if we try to find the autocovariance function, we can use the properties that the random processes have, like zero mean at one point. So uh, autocovariance function I can define as the expectation of the random process Gn with its mean value, right? So at a certain time instance. So autocovariance function, we need to define for two different random, I mean, time instances. Let's say it is n1, right? So autocovariance between n1 and n2, we can consider here. So if you are trying to find those two instances and their autocovariance, we need to define it as the expectation between gn1 minus mu n1 into gn2 gn2 minus mu n2. The autocovariance function, this is defined as the variance values, taking the product between the variance values and taking the expectation of that expression. So if we consider this first instance, gn1 minus mu n1, I'm taking the, the difference between those two terms, and I'm going to multiply with the gn2 minus mu n2. So this will give me the variance, autocovariance between the random processes, uh, two time instance. So if I want to find this out, I will have to substitute n1 in the initial expression. In here, I have initially expressed gn as a sine omega naught n, and then plus b cos omega naught n. That for that I need to substitute n1, and then I need to subtract the mu value. The mu value is of course zero, right? So mu value is we have defined, right? Mu value of the random process is zero, right? For any time instance, it would be uh, we can actually consider that since the random processor's mean value is zero, the mean value at time instance n1 is going to be zero. Mean value of time instance n2 is also going to be zero. Do you have any questions up to that point?
Question, ma'am. So we are considering covariance for N1 and N2, and
Yeah.
since the um, variables are independent and they are zero mean, so that n1 will be equal to n2 for the simplification of the calculations.
N1 and N2 are different, two different time indexes.
No, to find out the gn, uh, since this is independent, are we going to compare n1 and 2 and then uh, assume that they are equal?
Why do we assume that they are equal?
For the simplification of calculations.
I don't understand what
No,
you want to
I am trying to
say.
understand for the covariance why we are considering N1 and N2 rather than getting just with the GN.
So covariance is like, uh, sorry, auto covariance in
What the
here.
covariance? Yeah.
It's like you're comparing two time points in the random process and in a single, like, let's say you consider all the different realizations. In that
Okay.
in that case, you are considering three realizations.
Okay.
Let's say first realization, second realization, third realization. And then in here you have a certain time instance n1.
Okay.
And then you need to compare the uh, variance with another time instance. So you have to compare with another time instance. So it
Yeah.
can be equal to n1, but it can also be different to n2, n1.
Okay
There
then.
could be
Okay.
other instances.
Okay. I
So
got
you
you.
need to
Thank you.
consider all the cases. N1 equals to N2 and also N1 different to N2. Most of
Okay.
the time, when we are trying to find the autocovariance, we have to find the autocovariance in the case where N1 is not equal to N2. They are different.
Okay. I understand. So usually we try to find out for both of the instances. Uh,
Actually, if we want to find this one where the instance is equal, we need to define that. Like we need to specify that we are going to find the covariance of the same time instance.
okay.
We
Okay.
need to
Okay.
specify that. Uh, Most of the time, we find it for the different time instances.
Okay. Okay. Thank you, ma'am.
No problem.
Okay. Thank you very
So
much.
in here, the GN1 and GN2 will be different, and they will correspond to different time instances. And you need to simplify this expression based on that. So you need to consider the GN1 and its properties. And since the mean value is 0, you can make it 0. Then you need to consider GN2, and then you need to take the product between these two, and then you need to take the expectation. So after doing all this, you need to get a certain expression, and that expression is the one that correspond to the autocovariance. However, like finding this expression is kind of tricky. So that is the difficult part in this question. So I think that I will ask you to find the product between these two expressions on your own. But in the meantime, I will ask you to consider several things when you are trying to calculate that one. If you need to substitute n1 to the expression that we have. Um Basically, uh, you have to take the product between uh, the sign values and cos functions in here. So this is the function that we are considering. So gn1 means a sine omega naught n1 and b cos omega naught n1. in here you will have to take the cross product between cross multiplication between these terms. You will get four terms. Then you need to simplify that using the uh, theories related to a cos A cos A cos B multiplications, and how you can divide that into A plus B terms and A minus B terms. Likewise, you will get sin A sin B terms, cos A sin B terms. Likewise, you will get some products between cos and sines. These you need to further, simplify using the A plus B, theories. Uh, so you have some equations that you can use to get them into two additions of two functions. Let's say cos functions, sine functions. Likewise, you can get it as additions of two cosine or sine or cos functions, as I remember. So you can use the mathematical uh, functions that are defined in trigonometry related to this. I think, as I remember, or else you can find those equations as like mathematical definitions in anywhere, I believe. So it is a mathematical expression regarding the trigonometric functions. So by using these theories related to trigonometric functions, you should be able to find the simplified versions uh, of these expressions. Anyway, you need to find some kind of a final term that correspond to the autocovariance value. So this, whatever the term that you get, will give you some idea regarding the autocovariance functions behavior with respect to the time index n. So if this expression has some kind of a impact on, if the expression that we get here, let's say that expression that we get here is some kind of a function that is having the impact of n, then you will be able to, discuss that in the next part, where you discuss whether this GN random process that that we had in earlier is a wide sense stationary process or not. So in order for us to show that a certain random process is a wide sense stationary process, we we need to uh, we need to have the mean value, uh, autocorrelation value, or you can use autocovariance value instead of autocorrelation to uh, prove the uh, behavior of the uh, autocorrelation value. So you can use either autocorrelation or autocovariance. Here we used in this sum autocovariance. If you can show that autocovariance value does not depend on n, uh, does not depend on the index n. If you can show that, since mean value is already 0, and if this autocovariance value also doesn't depend on the time index n, which is the variable in this random process, then we can say that this random process is a wide sense stationary process. So if the statistics don't depend on the time instance, specific time instance, we can say that it is a wide sense stationary process. So we in here we consider only mean value and the autocovariance value, which are statistics of order first order. Mean value is a statistic of first order. Autocovariance value is a statistic of second order. So we consider statistics only up to the second order in this situation. And because of that, by looking at these two variables, mean value and autocovariance value, we can only say up to the second order statistics. We can only say something about the second order statistics. If they are not related to n, and if they don't depend on n, we can say that the process is a wide-sense stationary process. However, if they do vary with the time index directly, and then we cannot exactly say that it is a wide-sense stationary process. So I would leave you to solve this problem. So we can maybe discuss this in the next class if you have a question related to the obtaining the answer. So uh, I think what is left for us to do basically is that we have to find the exact expression for the covariance, right? That is the challenging part that is left for you to do. Uh, so you need to obtain this value or autocovariance, the expression. By looking at the expression, you can say whether it depends on the value n or not, whether it depends on the time index or not. So if it is not depending on the time index, you can determine whether it's a WSS process or not. So is it okay for you? I hope it is okay for you. If you face some more troubles with this, we will discuss about this question ahead as well. So it is not an easy problem to like solve just by looking at it. We have to think, and we have to understand about each of the variables that are in place uh, in this question. Uh, and we need to understand like how to solve that using the given information. So with that, I think I will discuss about, I will end the discussion about this question. So with regard to mean, I think we have resolved the questions. So because the random variable A is the independent random variable, we are able to consider that random variable as a separate random variable, and then take the expectation of the random variable A, and then take the multiplication with the sign omega naught n. Once we take the, uh, once we do that, once we consider the A and B to be zero mean, we so that we can equate, or we can simplify this expectation value to a zero. So whenever, even when we have a value for the cost values, we will get we will have zero value for the expectation of the random variables which are A and B. For A and B, we will get the mean as zero. So even though we have values for the sine omega naught n, which will be deterministic values, those will be cancelled out and they will not be considered as the final answer. So the final mean value will be zero, therefore, and the random process, for the random process Gn, the mean value will be zero. So for the autocovariance value, you need to find the autocovariance value. Since the question asks that specific statistic, you need to find the autocovariance value. And when you're finding that, you will be able to make the mean value of the random process zero, because we earlier found out that the random processes mean value is zero, and therefore uh, the uh, the values of the mean can be considered, can be neglected in this covariance expression. Then whatever the left with uh, expressions, but the leftover expressions will be considered, and they need to be simplified further in order to say exactly whether the autocovariance term relies on the index n or not. After that, if it relies on n, you can say it is not a WSS process. If it doesn't rely on the index, then you can say it is a wide sense stationary process, and it doesn't rely on the time index values. So, so with that, I will ask you to do the rest of the calculations when you have free time. Then I want to discuss about the power spectral density of of random signals. So when we consider about random processes, we have two main domains that we will be considering about. So I think in MATLAB simulations also, I have shown you that random signals can be discussed under time domain and under the frequency domain. So when we talk about the frequency domain, uh, we use statistics of power spectral density to decide the characteristics of the frequency domain behavior. So we use power spectral density as one of the metrics to determine the power of frequency components that are there in the random signal. When we talk about the time domain signals, time domain statistics, we discussed about the mean value or the average value, variance value, autocorrelation value. Likewise, we discussed about uh, statistics that we can compute in the time domain. So, mean variance autocorrelation and such kind of statistics are statistics that we can compute in the time domain. However, we also want to discuss and find about the frequency domain behavior of the signals. So that is also important, mainly because if you want to if you want to if you want to do some filtering of the signal, we have to find out the power spectral density of a certain random signal, and we need to find out like what are the frequency components that are dominating the signal, right? So in like random signals, let's say like I would like to consider scenario of random uh, I mean a situation where we can have several signals generating at the same time. So if we have a very sinusoidal signal with a certain frequency, let's say with a smaller frequency or like a lesser low frequency, and if we have to another signal with a high frequency, we have another signal with a high frequency, and if we have the combination of both the signals occurring at the same time. So if we have like a signal with like a very high frequency, the number of cycles per second will be low, high will be high, and the signal will have close by occurring, uh, you know, signal. So let's assume this is having high frequency, and this signal is having low frequency. So in cases where these two signals are getting combined due to some reason, right? And we receive a signal at the output, which is a combination of both these signals. So we receive some kind of a signal, which is a combination of both these signals. So if we take the combination, it could be some different signal, which is not equal to the initial signal that was generated and the combined signal can have some ups and downs and some kind of amplitude differences than the initial signal. So there could be lower amplitudes, higher amplitudes. Likewise, there could be some deformations in the final signal. So there could be some deformations in the final signal. The final signal can have high amplitudes or low amplitudes likewise. And in the final signal will not be equivalent to the original signal. So the receiver might want to separate out these original signals from this final signal. So if you want to get back these two signals separately, right, again back in the normal state, we need to do some processing at the receiver end, right? So if you want to find exactly the original signals we had earlier, then we need to do some processing in this place. So in order for us to do this, separation of the signals into different signals, we need to find out like what are the dominating, frequency components in this combined signal. So if we take this combined signal that we consider here, right? So in that case, like we will have, if you take the frequency domain, we will need to consider the power spectral density, right? Power spectral density against the frequencies. So when you consider the frequencies as the domain, X domain, you will have different frequencies, F1, F2, likewise. So if we consider these two signals to have frequencies F1 and F2, there will be some power related to this F1 frequency in this plot. Once we try to measure using some kind of a spectrum analyzer, we can observe using a spectrum analyzer. Uh, we can observe the amplitude of the signal under each frequency component, right? So the signal can have frequency, some kind of a specific frequency, and under that specific frequency, the signal power that we can observe, we can see in this power spectral density plots. So for F2, we will have another, some kind of a signal power, right, that correspond to F2 frequency components, which means that in the combined signal, we have basically two main signals which have F1 frequency and F2 frequency. So by looking at this PSD plot or power spectrum density plots, we can see what are the dominant frequency components in a combined signal or a combination of random signals or a certain random signal. So we can see the frequency components specifically using the spectrum analyzer. So under each frequency component, you can see the power of each of power that is exhibited by that signal under each frequency component. So apart from that, in between these, in these, in the in between places, there could be some frequency components which are of low amplitude, but those signal components will correspond to interference that is generated in the system or noise that is generated in the system once we combine these two signals together. Okay, so when there's some combination happening between two different signals, due to the indifference between the signals, uh, could there could occur some noise signals or interfering signals, which cause the frequency components to be added to the system or removed from the system. So anyway, like some additional frequency components that were generated are also observed in this PSD graphs. So if you have any questions, you can ask. So that is basically regarding the power spectrum density. And that is important for us to find out the uh, component or signal component in the frequencies in a certain signal. And so this is basically regarding the basic idea of the signal of the power spectral density of a certain signal, right? So apart from that, using the theories that we have received and we have learned in the class, we have some definitions that we can define for the power spectral density of a certain signal, right? Of a certain signal. So power spectral density can be defined as the uh, yeah, power spectral density can be defined as the metric that defines the power of a certain frequency component in a certain signal. So we can use this to measure the of a power of a signal, measure power of each frequency component, right? In a random signal. So we can measure the power of each frequency component using the power spectral density. So power spectral density is a function that allows us to determine the energy of a signal. So I mean, power means like it gives us the power value. By using these power values, you can find the energy of the signal as well. So another thing is that this power spectral density is defined over the frequency domain. So the frequency domain, uh, I mean, power spectral density is defined over the frequency domain means that whenever you have a PSD curve, it will be against the frequency. So the normal notation that you will be using for power spectral density is capital S, and if there's a random variable X, you can use XX and then F, which means that power spectral density of the random process X against the frequency F. So the plot will be against frequency domain. And in here, the frequency components will be defined in this axis. And whatever the power value of all of the signal under that frequency component will be defined in here. And it can be defined using either dBm, dB, or watts. We can define this X value. We can define either dB, dBm, or watts. So the value of the frequency component's power is given by this plot. So in in our in the theories that are presented by scientists have mentioned that the power spectral density is the power per frequency component, right? So power spectral density is the power per certain frequency component. So this gives us the power per certain frequency component. So you can see that the units of this will be watts per hertz, right? Watts per hertz, right? The units will be watts per hertz, like power per frequency. So when we try to see some other relationships we can see that for uh, right. So when we consider um, the when we consider the autocorrelation function, right? When we consider autocorrelation function of a certain random process, right? And if we try to find out the autocorrelation function of a certain random process, right? In that case, we can equate that to power spectral density, and that is another theorem that is defined, and we will discuss as that as the next theory. So it is known as Wiener Khinchin theorem. So this theorem tells us about the relationship um, uh, between the autocorrelation and the power spectral density. So Wiener Khinchin theorem. So this Khinchin theorem. So this theorem relates the power spectral density XXF with the autocorrelation function. So power spectral density value will be equal to the integration of the autocorrelation function that we define, let's say between 2 points with time difference tau, and we can do the integration over e to the minus j 2 pi f tau and d over d tau. So by doing so, it is proved that this PSD is equal to this integration. So this integration is actually the definition of Fourier transform applied on this autocorrelation term. So the uh, so basically, you need to apply the Fourier transform on autocorrelation function to find out the PSD value of a certain random variable. So, so this relationship is known as the Wiener-Khinchin theorem, and this is a very important variable, kind of a result. So you might want to remember this one, and it will be used for different multiple sums related to this, you know, this domain. So this is the equation that is required to find the power of a certain frequency component using autocorrelation function. So once you know the autocorrelation function, you can apply that in here, find its Fourier transform, and find the PSD value in terms of that Fourier transforms units. So we will discuss about the Fourier transform and how it works in the next class as well. But however, like we just need to know here that we need to apply the Fourier transform to find the spectral density. If we have the autocorrelation function, so you need to use the Fourier transform operation. So Fourier transform is done basically here by this integration. The integration value is basically done. Is done by taking the product with the autocorrelation function, this term, right? And then doing the integration over these limits where the signal is defined. So when we talk about the properties of the, power spectral density, right? Properties of the power spectral density, we can, uh, right? So apart from that, I think that we will discuss uh, some o- some points that are obvious, right? So if there's a signal, right? If there's a signal which is which is fluctuating very much, right? If there's a signal which is fluctuating very much, let's say it is having its amplitudes fluctuating at each time instance very quickly and then in a very random manner, uh, and if there's a signal that doesn't change its values, so it's very smooth, let's say it's like a sinusoidal signal which does not uh, have I mean random fluctuations much. So in here we have, so in this first signal we have the random fluctuations, and so this random signal that we can have with this lot of fluctuations, we can see that the similarity between one point in the graph and another point in the graph are less. So if we take this point B and if we take this point A, the difference between A and B is high, right? Whereas like in let's say like, sorry, if we take two peak points, let's say B, if if this is A, you can see A and B are different. However, if we take B here and if we take another peak point A, we can see that there's some similarity in here. So if the so what we can observe here is that like if we have like frequency changes, or if we have a signal where the fluctuation is very high, then we can see that the autocorrelation value is low. If the frequency is low, then autocorrelation is autocorrelation is high. So what I mean is that if the frequency of the amplitude change is low, in as in the second signal, in here autocorrelation value can be we can have high autocorrelation values. In here, in the first case, uh, if we have a lot of fluctuations, then the frequency of the signal is high. And also, once we take the autocorrelation value between 2 points, we can see that the autocorrelation value is also low. So the similarity between these 2 points, A and B, is low. So if this is low, uh, then the autocorrelation value also goes down. So autocorrelation value gives us a similarity between 2 points in the signal. So similarity increases when we have low frequency and also similar points in the random signal. So that is basically regarding uh, how the autocorrelation actually affects the power spectral density, right? So power spectral density defines how much of power is there in a certain signal. So if there's a lot of correlation between 2 points, then the energy of related to that point increases. Uh, so uh, so when we consider uh, when we consider scenarios where we have uh, where we have the uh, this expression, right? This autocorrelation function expression, and then if we substitute the time as tau equals 0, right? We substitute xxf and tau equals 0 in here. That means we are considering the same time instance in the original signal, which was in the time domain, right? So if we have situations where we want to consider the power of a certain signal at the same time instance, we need to make this tau equal 0, right? So tau is the time difference between the two positions in the signal, right? So tau can be some kind of a time duration between the 2 points that we are trying to compare with. So this tau value needs to be 0. It needs to be made 0 if you want to analyze and study only one point uh, in the in the in the signal. So if you want to consider only one point in the signal, then you need to make the tau equal 0. After that, you can find the power of the signal using this expression. So um, basically, that is regarding the autocorrelation function and how we can relate the autocorrelation function to the power spectral density of a certain random signal. So when we talk about another situation, we can consider white noise, right? A random process uh, which is called the white noise random process. So white noise. So white noise is uh, uh, like a signal, a random process that generates noise that can affect our desired signals in our applications. So this white noise can destroy or can harm the signal, the original signal in the system, right? However, like we need to therefore know about the behavior of the white noise in order to remove the effects of the white noise. So white noise can be a noise signal uh, that we receive over the time, and normally the white noise is a randomly fluctuating signal, and it is so this noise signal can take some values as its amplitude. It can also have negative plus or minus amplitudes depending on the its direction. So I will draw the right noise as the random signal that has fluctuating amplitudes. So the this white noise process is um, is an important process that we need to know in order to remove it from uh, our signals that we receive at the receiver end. So if I want to find the power of the white noise, I need to find the autocorrelation value, right? And then once I find the autocorrelation value, I will be able to plot the power spectral density curve. So in order for me to find the autocorrelation value of the white noise, I need to obtain the autocorrelation value by taking the product between 2 points in the in the random process. So there could be two points T1 and T2, right? So we are going to compare these T1 and T2 points, and we are going to find the similarity between those 2 points. So the value of the noise in this T1 point we can take as N1, and then value of signal at T2 position we can find as N2. And if we try to find the expectation value, you can find it by getting the value of N1 and then N2. N2, sorry. So if uh, we are trying to measure the amplitudes of the signal at two time instances. So the two time instances that we are considering are T1 and T2. Let's say the time difference between T1 and T2 time instances will be tau. Right? So the exact time difference between these 2 points will be tau. Then once we take the amplitudes of the noise signal in here, right? So let's say this noise signal is N1T, right? And this is the time domain axis. So the N1T at certain time instance T1 will be compared with N1 T1 plus some kind of a tau value. And then So we want to find this value, and then once we compute it, we can make the we can we can see how the power spectral density is defined. So um, so basically this is a random process, and these two uh, instances are independent to each other. So since these n1 t1 and n1 t1 plus tau are independent to each other, I will be able to consider that these can be written separately. So once I do that separately, I will also be able to uh, consider that the variance that so uh, actually for the white noise scenario, since there's no like correlation between two different time samples. So since there's no correlation between two different time samples, T1 and T2, it is basically the autocorrelation function is basically defined as n naught over 2 and tau uh, delta tau. This is a definition that is defined for the white noise, which is a standard definition. So this is the standard definition regarding the autocorrelation function, right? Uh, so a certain value for this autocorrelation function comes only if there is some kind of a delta function that defines a value at the tau equals 0, which means that the autocorrelation function value has uh, autocorrelation of a white noise process has a value only at this point where the tau value is 0. It can be 1, tau value can be 1, 2, 3, something like that. And it can also take minus values. But only if the time tau value is 0 only, there's a certain value for this autocorrelation function. So in white Gaussian noise process, this is the situation, and you have to consider the fact that there's power only at the place where this tau value is 0. So what we mean by tau value is 0 is that uh, the time instance that we are considering will be same, right? So t1 equals t2. Only if t1 equals t2, there's some value for the tau. Otherwise, in all the other time instances, the value of the signal's power will be 0. So the autocorrelation function has the value only at the place where tau equals 0. So when we consider this for the power spectral density is the Fourier transform of this autocorrelation value. So Fourier transform of this autocorrelation value, which is tau delta tau. So Fourier transform of this autocorrelation functions value will give me the power spectral density of that signal. So power spectral density of the white noise signal uh, can be found uh, by this Fourier transform of the autocorrelation expression. So the autocorrelation expression, uh, uh, so if we take the Fourier transform of this expression, what we will be left with will be only n naught over 2. So by taking that into account, I can define and plot the white noises power spectral density as n naught over 2. So power spectral density value will have a certain constant value n naught over 2 over all the frequency components. So this will be a constant value which does not change over all the frequency components. So what we mean here is that the power under each frequency component will be constant, and it will be equal to n naught over 2, right? So if I want to find the power of this white noise, the entire power of this white noise, I need to find the area under this curve, right? In order for me to find the power of this signal, I need to find the area under the curve, right? And I said that this area or this curve goes from one end to the other end. So this curve is an infinite curve. It goes from 1 minus infinity to plus infinity. So this signal goes up to infinity. And in this side also, in the left side also, it goes up to minus infinity. If that is the case, right? Do you think that such kind of a signal is realistic in the real world? Right. So by definition, I mean this is a some definition that has been made. Right. So regarding the white noise, so the white noise has a power spectral density like this. The power spectral density of the white noise is having a constant value of n naught 2 over all the frequency components possible up until frequency is infinite. So if it is the case, and if we take a certain area underneath the curve, if you give us some area, and that area will correspond to some kind of a power that can be generated from that signal, right? So if we take the area under the curve, we can find the power of that signal. However, like white noise processors, they have this infinite line of constant line up to infinity. Do you think that this kind of a white noise process actually exists in the world? Right. So with that question, I think I will start the quiz, right? So I have a quiz prepared. So I will give the quiz. So I want you to know that like white noise processes are defined in theory only, and this white noise process cannot be available in the actual world because the if we take the integration of this curve under the curve, then the integration will equal to infinity. There cannot be any random processes that has infinite power. So therefore, this is a theoretical assumption only, and it's a white noise, it's called as white noise random process, right? So white noise random process is a theoretical assumption only, and it is used for different mathematical modeling and all, but it is a theoretical one only. It is not realistically possible, right? So if you have some questions, you can ask up to this point. So I want you to join this quiz if possible. The link I have shared in the chat, so please join in if possible. So you can join the quiz and let's do the quiz. And I think that we were discussing about some theory during this class. In case that we need to discuss more about the theories, we can do that during this quiz. So I think the quiz will enable you to think about some conditions or some theories in a different manner. So thanks. So others also can join with your index number, registration number. Are there any students to join? And if there are some more students to join, you can let me know in the chat or you can speak. So I will wait for maybe 2 minutes. Okay, I'm starting. Look at the screen and you can see the question in the screen. And then, you can give your answers in your device. White stationary process is a random process that implies the mean and variance are constant over time, decreasing over time, increasing over time, undefined over time. Yes, so first answer is the correct one. Because wide sense stationary is the process that has the mean and variance constant over all the time instances, right? Time variables. So constant over all the time variables. So sense stationary, wide sense stationary process is what we are discussing about in here. Okay, so I think yes, let's go ahead. In an ergodic random process, ensemble average is equal to yeah, the time average of a single realization. So ergodic means like we equate the averages along the ensemble to the average of a single realization, time average of a single realization. So if you have any questions, you can ask. Yes, so integration operation is used on top of the autocorrelation function to find the power spectral density of a certain uh, signal, random signal. So I discussed with you about the Fourier transform, right? The Fourier transform of autocorrelation function being equal to the power spectral density value. So in there, actually, when you do the Fourier transform, you're actually applying the integration function over the autocorrelation function or the autocorrelation value. Then you do the integration actually on top of the autocorrelation value. So the integration is therefore is used to find the power spectral density. And you can use the integration operation on top of the autocorrelation functions value. So, which is the true statement regarding power spectral density of white noise. Okay, so many of you have got the correct answer. So white noise, I think I discussed just a while ago, has power over all the frequencies, and the power is constant. It's n naught over two, and it is constant n naught over two over all the frequencies. So white noise is something that has power over all frequencies. So this is asking about power spectral density and the area under the power spectral density. What does it give? So, so power spectral density uh, is a function, right, that defines us the power of the signal, right? So power spectral density gives us the power under each frequency component, right? So if we consider different frequency components in a certain random signal, for each frequency component, the power for all those components, power for each of the frequency components is given using this power spectral density function. So if we are taking the area under the curve, then you will get the average power. If you take the integration, you will get the average power uh, for of the process. So if you take the integration, you will basically get the average power of the signal. If it is not clear, you can ask. Yes, so many of you got it correct. Power of each frequency component in the process or the signal is given by the power spectral density values. So the white noise process has infinite power and hence not physically realizable. Is this true or false? It is true, right? I mentioned to you about the white noise process having infinite uh, power. Like if you calculate the power underneath the white noise process, uh, the power density, power spectral density function, it will be infinite. It will give us infinite power because the curve doesn't end. It goes up to infinity. So if you take area under an infinite curve, then you get infinite power, and infinite power is not realizable in the world. So white noise process is something that is theoretically defined for mathematical purposes. So it is used in some cases where we do make some assumptions regarding white noise presence in a certain process or in a certain environment, right? In a certain application. But the actual presence of white noise is not something that is in the real world. It is a theoretical assumption. Yes, so the yeah, so I mean this is asking something very simple. So in the power, the power spectral density is defined against the frequency, right? Power spectral density is defined against the frequency. So the variable is the frequency. So power spectral density is uh, uh, like studied under the frequency domain. So under each frequency, you define a certain power. So that is what's happening in the power spectral density function. So I hope it's clear to you. If you are not sure about that, you can let me know. Right. So I think uh, I will publish the results that you have obtained in the LMS website. So thank you for participating in the quiz. So and I will publish the marks in the LMS. Right. So if you want, I will put the questions also in the LMS.
That's a very tricky question, to be honest.
Do you have questions, Gayan?
No, just saying, it was very
I
tricky
cannot hear
questions.
you. Can you speak up?
Oh, you cannot.
Yeah.
Just give me a second. Can you hear me?
Now I think it's fine, but I think it's there's echo then.
Uh,
Anyway, you can tell me.
how about now? No, sorry. Can you hear me now?
Yes.
Okay, I'm sorry. Uh, just saying, the questions are tricky, to be honest. I couldn't answer two or three of them. Missed those. Anyways,
Yes.
thank you. It was fun.
Okay. So I think I just made the questions based on what we have covered in today's class as well. So I think it's going to be challenging when that's the case. But I just wanted to just so from the quiz actually I'm giving some bonus marks, not the direct marks to the final grade. So if you come to the quiz, you can get some bonus mark, and just it I hope that it enables me also to give the information in a different manner and not using the lectures and doing the lectures, but in a different manner and like discuss if you have any concerns, discuss those facts during that time. So I think that this quiz marks will not directly impact you, but this will be a bonus mark. And when you face the exam, also sometimes it might be kind of useful to you. But in the exam, like most of the time, you will not get a quiz like this. You will get maybe some, like essay type questions. So you don't have to worry even if you fail and you don't get marks, it won't directly impact your final grade. Um, but these questions are, I think, important for you to refresh the knowledge. So for every session that I'm doing, I'm hoping to give these questions and share those questions with you, and such that you can, like keep up with the theory that we are covering in the class. So that's all from my end. If you have any questions regarding those quiz questions, we can discuss. And I will share the marks in the LMS, and also I will share the questions in the LMS if you want that, so that you can check the questions and the answers, and it will make you enable to go through the theory. So that's all from my end for today. So if you like, you are free to leave. Otherwise, you can stay and you can ask any concerns or any questions if you have. You can ask. So thank you so much.